Welcome to this explainer. We're jumping right in today because we've got a fascinating and honestly, slightly terrifying mathematical mystery to solve. We are going to act as data detectives, looking under the hood of the exact algorithms that are supposed to keep our skies safe. And as we unpack this highly publicized and tragic aviation event, we're going to uncover a hidden structural flaw. But here is the truly mind-bending part. This exact same mathematical blind spot, it isn't just in aerospace. It spans across multiple modern industries, from the finance sector to genomics. So let's get started.
To understand the math, we really have to understand the event itself first. Imagine it's May 21, 2024. Singapore Airlines flight SQ321 is cruising along at 37,000 feet. Suddenly, without any warning, it hits severe clear air turbulence. The numbers here are just staggering. The aircraft plunged 54 meters in mere seconds. It was a harrowing, incredibly violent drop that left 104 people injured and, tragically, resulted in one death. Now, this wasn't some massive dark storm system you could see out the window. This was an invisible, highly localized wind shear anomaly.
If we look at what was happening over the Andaman Sea at cruising altitude, it paints a pretty clear picture. The red and yellow gradients you see indicate wind speed, and those little arrows are tracking the wind vectors. Right there in the center, marked by that blue star, is exactly where flight SQ321 hit the turbulence. The location is absolutely crucial here. The flight was over the open ocean, which is a notoriously data-sparse region. I mean, there are very few weather balloons or observation stations out there compared to over land, right? But even with sparse data, modern meteorology is supposed to be robust enough to fill in the gaps. And that brings us to the million-dollar question of our investigation. Modern numerical weather prediction uses these incredibly sophisticated operational models. These are the gold standard systems literally designed to forecast these exact types of atmospheric hazards and keep flights safe. So, how did they completely fail to see this deadly event coming? To solve this mystery, we have to look at how these models decide what data to keep, and more importantly, what data they throw away. We're comparing two very different mathematical approaches. On the left is the traditional operational approach, the ensemble common filter, or NKF. To save on massive computing costs, it takes a shortcut. It uses a limited rank 49 ensemble, which is basically just taking 50 broad samples to guess the weather. On the right, we have a framework called MPDOK, which takes a totally different path. Instead of a small sample, it uses a full rank 578 Matern kernel. That's just a mathematical way of saying it processes the complete, complex picture without taking any shortcuts.
The exact problem with that shortcut is laid bare right here in the eigenspectrum, which maps out the full spread of atmospheric variance. See that black line? That represents all of the true atmospheric variance. But the NKF model draws a hard line at 50, right there on the left. That entire red zone on the right visually illustrates how the NKF acts as a low-pass filter. It perfectly captures smooth, large-scale weather patterns, like massive high-pressure systems, but it completely deletes the sharp details. It literally discards 91% of the mathematical modes. And guess what lives in that discarded red zone? The sharp, localized wind shear anomalies, the exact turbulence that hit SQ321.
Believe it or not, it actually gets worse. Compounding this mathematical blind spot is something called the Gaspari-Kahn localization dead zone. You see, because the NKF model uses such a small sample, it generates statistical noise. To fix that noise, meteorologists apply a patch, a hard cutoff radius of 1,000 kilometers. If an observation station is further than 1,000 kilometers away, the model just assigns it a weight of 0. Over the Andaman Sea, where SQ321 was flying, this shortcut literally forced the model to ignore 28 out of our 30 observation points. It intentionally blinded itself to the surrounding data. And the notebook results we pulled on this, they are the absolute smoking gun. Because of those two math shortcuts, the low-pass filter and the localization dead zone, the NKF model assigned a functional zero common gain of 0.005 to the SQ321 location. Common gain is essentially how much the model trusts and uses new data. That means the algorithm entirely rejected the incoming information. It recovered just 0.1% of the background error. It was flying completely blind. But by using the full kernel and not throwing data away, the MPDOK framework recovered an undeniable 61.6% of the error. Its data acceptance rate was nearly 400 times larger than the traditional models. When you look at these two error maps side by side, the stark reality of these choices is just night and day. The NKF model generates this massive localization dead zone, that large red circle where the model is completely paralyzed. Inside that zone, exactly where the flight is marked, it has no data and makes 0 corrections. But switch over to the MPDOK map, and that dead zone totally vanishes. MPDOK smoothly connects the data across the ocean, pulling information from distant observation points to clearly reveal the hazardous anomaly right where the flight encountered it. Okay, so we found the mathematical culprit for this specific aviation failure. The algorithms meant to protect us literally filtered out the danger just to save on computing power. But here's where this investigation takes a mind-bending twist. We really have to ask ourselves, if this standard mathematical shortcut is failing so spectacularly in aerospace, does this error exist anywhere else? And the terrifying truth is, yes, it absolutely does. Completely unrelated industries are using the exact same low-pass filter shortcut to save computing power, and they are suffering the exact same blind spots. In genomics, algorithms use a shortcut called the APY method, which perfectly predicts common traits but completely hides rare disease variants. In mining, fixed-rank keying maps out general ore bodies but totally misses localized, high-grade deposits. And in finance, portfolio optimization tools cap their correlation graphs, entirely missing indirect asset crashes. The domain changes, but the mathematical failure is identical. Now, you might be sitting there thinking, well, hey, computers are getting faster every day. We'll just increase the sample size. But mapping the performance in both aerospace and genomics proves that just doesn't work. Look at how the performance flatlines, saturating its structural limits. Adding more ensemble members to the weather filter doesn't lift it out of the dead zone. It still clamps it to zero. Adding more core animals in genomics still hits a ceiling. Just throwing more raw computing power at the problem won't fix it, because the flaw is deeply architectural. You simply can't process data you've structurally decided to throw away. If you take away just one thing from this explainer, let it be this. In our rush to build efficient, scalable models, we chop off the tail of the data, casually dismissing it as statistical noise. But that discarded tail is not noise. In aerospace, it's clear air turbulence. In genomics, it's rare genetic diseases. In finance, it's the black swan event. The data modern algorithms throw away to be efficient is exactly where life and death anomalies reside. Knowing that modern industry applies this blind spot to almost everything completely shifts how we view the algorithms running our world. Whether it's the route your next flight takes, the way your retirement investments are managed, or how cutting-edge medical treatments are modeled, this low-pass filter is likely right there, smoothing over the critical details. It leaves us with a profound question to consider today. What other critical anomalies are currently hiding in the discarded mathematical tail of our most trusted systems? Thank you so much for joining me on this explainer. Keep questioning the data, and we'll see you next time.